Hello students, we will start with the chapter of oscillation, which covers these topics: periodic motion, oscillation. Then we will move to simple harmonic motion, which is a typical simple oscillatory motion. Then we will move to a few words on free motion, damped motion, forced vibration and resonance. Now, if all of you are aware of the linear motion, projectile motion, circular motion, rigid body rotation, all these things you have already read. Now, this is a different kind of motion. See, gradually we are coming from very idealized motions, linear motion, circular motion, all these are very ideal motions. In nature, in day to day life, we very rarely come across such motion, but we can always consider them to be very nearly linear or very nearly circular motion. But these oscillations or periodic motions, these all are more towards the nature. In the nature, you will come across many instances which are periodic, which involve oscillations. So, in all around us, when we are talking about sound wave, so it is a sound, there also there are some oscillations of the medium, of the air medium in which I am talking. So, all these things are actually very real physical world. You will come across oscillations everywhere. You are hearing a music is nothing but consists of oscillations, vibrations of the string produce oscillations in the air, and that produce a music. So, noise, music, all these things actually involve oscillations or vibration of some kind. So, that is why we are reading periodic motion, oscillations, all these things. Periodic motion. So, you already know about the motions, different kinds of motions. I can segregate them into two classes, periodic motion and non-periodic motion. A non-periodic motion, a periodic motion is a motion which repeats itself after equal interval of time. It repeats itself. That means, the same thing is repeated after a certain interval of time, the same path is repeated by the body. For example, the case of simple pendulum, if I take the case of a pendulum, a simple pendulum is suspended from a rigid support. I take this bob to this side and leave it, something like a swing. You would bring this body to the side and leave it. So, what happens that from here it will move to this place, it will go to this overshoot, it will not stay at the middle, this portion, because it has already acquired a large velocity. The velocity cannot become 0 instantly, and that is why it overshoots to this side, and gradually the velocity decreases, and here the velocity becomes 0, it comes back to the original. Again it overshoots to this place. So, from here, from position A to B to C, back to B, back to A. Then again it repeats A, B, C, C, B, A. So, A, B, C and B and A, this motion is repeated again and again. After a certain interval of time, if you take a stopwatch and find out the time, you will see that there are equal time is taken for one A to B to C and back to A. That time is always nearly same for the first 10 oscillations or 20 oscillations. This is the case of a spring. This is a spring mass system. So, the spring mass system also, in this case, a spring is attached to a mass m, and this spring is attached to a rigid support here. I move this mass to side, and let us say from here I release this. So, what happens that the spring tries to regain its original shape and size. So, it takes the body back. So, the body is moved to the, from here you have left by applying some force, by stretching the spring you have brought the mass here, and you have left this. Now, the mass will go to this point, it will overshoot, again it will go on, going this way it will compress the spring. When the spring is compressed, it will try to go back. So, from here it will go come to here, then it will come to this, and again back to this, again back to this. This motion is again repeated. So, it is a repetition of the same, body moves along the same path and repeats after a certain interval. So, this is a periodic motion. Similarly, take the case of a clock. Now, in a clock, you have, let us take the case of the minute hand. The minute hand rotates from, let us say, from this is 1, 2, from 2 to 3, 4, 5, 6, 7, 8, 9 and 12, 1 and then come back to 2. After 1 hour, it comes back to 2 position again and again it repeats, and every time it takes 1 hour to complete the one full circle. So, to go once, again the same path is repeated after 1 hour. So, the minute hand is undergoing a periodic motion. We say that it has a period of 1 hour. After 1 hour, the motion is repeated. So, this is also a periodic motion. Or you take a stone and you tie it to a string and then you rotate. So, the string is rotating in a circular motion. So, the string, if you are rotating it uniformly, it will go to this place, then it completes the circle and comes back to this position. Again the motion is repeated. So, this is also a case of periodic motion. But all of these periodic motions I have shown here are not equal, they are not same. The same periodic motion can be subdivided into oscillatory and non-oscillatory. Now, what is oscillatory and what is non-oscillatory? So, non-periodic motion, something like if you have a body which is moving in this direction, it has some acceleration, it is after some time it is here, it is continuing to move with some acceleration, the acceleration may be decreasing, increasing, and it does not matter, but it goes on. So, this is not periodic, it is not repeating its path, it is not coming back, or it is not repeating the same path again and again after certain interval. So, that is why I call this is non-periodic motion. Or your the case of projectile motion. When you are throwing a stone, it is going up and coming down, falling here. This motion is not repeated. So, a projectile motion of a stone when projected upward is also non-periodic. Now, out of the periodic motions, some are oscillatory, some are non-oscillatory. Now, oscillation, from this word you can understand what is oscillation. Oscillatory motion is the one in which body moves to and fro. The body moves to and fro about a mean position. So, it moves to and fro about a mean माने average, गोटे मझिरे गोटे पोजिशन अच्छी किसी गोटे एवरेज पोजिशन गोटे अच्छी तार मीन पोजिशन सेटा कह जोटा तार इक्विलिब्रियम पोजिशन जोठी से इक्विलिब्रियम रे अच्छी देयर यू हैव टू डिस्टर्ब इट टू स्टार्ट द मोशन. So, you have started the motion like the simple pendulum. This is my mean position, the vertical line is the mean position, B is the mean position. Now, if I move it to A and leave it, so it moves A to B, एपट को A पर्यंत जाइथिला, B को आसिला पुणी C को जीवो, C रु पुणी B को आसिला पुणी A को जीवो. ता माने B चारिपटे B रो टू एंड फ्रो आगकू पछकू, B रो आगकू B रो पछकू, टू एंड फ्रो, B अराउंड नुहे, अराउंड हे गला माने B चारिपटे बुलुनी से B रु A को जाउची, A रु B को आछी, पुणी C को जाउची, पुणी B को आछी, पुणी A को आछी, ताने B रो आगकू B रो पछकू, that is called to and fro. So, to and fro motion आगकू एवं पछकू गोटे मझी मीन पोजिशन रे आगकू पछकू से जीवो. So, this is a simple pendulum is oscillatory motion. Your spring and mass is also oscillatory motion. But these are ये स्टोन टा जदि एमती एमती होता तेबे मु कहि थांती oscillatory, किंतु स्टोन एमती जाउची पूरा सर्कल कंप्लीट कला पुणी आउ थरे सर्कल को कंप्लीट कला. सो इट इज नॉट मूविंग टू एंड फ्रो, कहार आगकू पछकू एमती गला भलिया नुहे, से गोटे डायरेक्शन रे जा चलीची. सो दिस इज नॉन ऑसिलेटरी मोशन. इवन द वॉच और द क्लॉक is the minute hand of the clock or the hour hand of the clock, both are non-oscillatory motion, but they are periodic because after certain interval of time the motion is repeated. So, since it is repeated with a certain time, it is called periodic, but it is non-oscillatory. Whereas, the case of simple pendulum and spring mass system I have shown here, both of them the body moves, there is a certain mean position to and fro of which the body is moving. That is why these two motions are oscillatory motion, and these two motions I have shown here are non-oscillatory. Now, from the oscillatory motion again, there are some motions which are simple harmonic and there are non-simple harmonic. Simple harmonic motion, we will go to that what is special about simple harmonic motion. In this case, the acceleration of the body is proportional to displacement. And directed towards the mean position. Such motion are simple harmonic motion. We will go into the details of that thing, and in those cases where the acceleration is not proportional, like these are non-simple harmonic motions. So, we will study about periodic. What is periodic? Now, motion which repeats after a certain equal interval of time, then periodic, then oscillation. What is oscillation? Then what is simple harmonic motion? These things we will cover, and you should know which is oscillatory motion is always periodic, but all periodic motion are not oscillatory, because this motion is periodic. Minute hand motion is periodic, but not oscillatory, it is non-oscillatory. So, but all oscillatory motion are periodic, all simple harmonic motions are oscillatory, they are also periodic. So, you understand the basics of this chapter, then we will go into the details of that thing. So, periodic motion is one which it repeats itself after certain interval of time, and this interval of time, the minimum, we can define a time period for a periodic motion. Time period is the smallest time after which the motion is repeated. For example, in the case of the minute hand of a clock, the minute hand of a clock is, the time period is 1 hour. Then we can define a frequency. For any periodic motion, time period, we denote the time period by a capital T. So, frequency f is equal to 1 by t. See, in t time, you are going one repetition in t time. So, in 1 second, the repetitions will be 1 by t. This is the number of repetitions. So, frequency will be the number of repetitions in 1 second. Is frequency, and f is equal to 1 by t, and t is measured in seconds. So, the frequency is measured in hertz. So, this is cycle per second called hertz, and it can be represented, the displacement of this periodic motion See, when we say displacement, it is not necessary that it is only position displacement. It refers to any quantity whose variation is causing that periodic motion. The variation displacement represent may be position displacement, it can be pressure variation, like in the case of a sound wave we have pressure variation. Pressure changes like periodically. So, somewhere it is compressed, somewhere it is rarefied. So, that is called a pressure variation. So, pressure variation may be represented as the may be called the displacement there, or in, for example, if you go to AC circuits, the charge on the capacitor in case of an AC circuit is also this can be called, it will also go through periodically, it changes, and we say that that variation is also a displacement. So, it is represented by a function, you can represent it by some function f, let us say f at time t, it changes from time to time. It tells me that the definition of periodic motion says that the motion is repeated after equal interval of time, and that time interval, time period, minimum time after which it is repeated is your time period capital T. That means, if whatever is the displacement at time t is equal to the value of the same displacement at time t plus capital T, because it will, after that it will be repeated. So, the function value of this displacement satisfies this. At time t तार value jaha capital T time pore t plus capital T time re तार value ta seya. So, this is represented by a function, and we call that the displacement function. So, now we move over to oscillation. When a body undergoes to and fro motion, I have already told you, to and fro motion about a mean position, we say that the body is undergoing oscillation. See, we also use the word vibration, many times vibration. There is not much difference between vibration and oscillation. Only difference is that the frequency, when frequency is large, we call it a vibration, otherwise we call it an oscillation. For small frequency oscillations we call oscillation, but when frequency is large, for example, if you have a guitar and you are the string is plugged and left. So, there the string vibrates with a large frequency, बहुत जल्दी तामाने बहुत थर से एक सेकेंड से बहुत थर वाइब्रेट करुची, that is what is the frequency is high. So, the frequency is high, then we say the vibration of the string, we do not say the oscillation of the string, but we say oscillation of a simple pendulum or a oscillation of a swing. So, there the frequency, the number of cycles it goes in 1 second can be seen and it is small. So, the frequency small thila bale ame taku oscillation कहूँ, otherwise we call it a vibration. So, that is the only difference, otherwise they both are oscillations. So, to and fro motion, for example, I have given you the example of simple pendulum and mass spring system and mass spring system. The mass spring may be horizontally placed or it may be vertically also placed. You have a spring vertically and a mass, and it is it goes down and go up and like this. The motion may be vertical or motion may be horizontal. Both are oscillations. So, in case of oscillations, what we will similarly we can define time period. We can define okay, better going to oscillations, let me come to directly to the simple harmonic motion. So, first of all, a motion which is periodic it is periodic, then in which the body moves to and fro it is oscillatory, moves to and fro about a mean position periodic means it repeats, the motion is repeated after a certain interval of time. The body moves to and fro means it is oscillatory, and third thing that its acceleration of the body is proportional to displacement, and directed, the direction is also important, and directed towards the mean position. So, if these three things are satisfied by a motion, the body is said to be performing simple harmonic motion. Periodic, oscillatory, and acceleration must be proportional to displacement and directed towards the mean position. For example, your simple pendulum, this is the mean position. I take the body to this side and leave it from here, it will come back to its mean position, overshoots to the other side. Go to from A, it goes to B, go to C, back to B, and A, back to A. Again that thing is repeated. It is moving to and fro. When the body is here, the weight is acting mg downward. There is a tension in the string. If this angle is theta, I can find a component of mg along this direction will be mg cos theta. This tension will be equal to mg cos theta, and what remains is mg sin theta. So, the force is mg sin theta, which is bringing it back towards the mean position. So, this is towards the mean position, force is towards the mean position means acceleration, force is mg sin theta. So, acceleration will be g sin theta, m re divide kar deli. So, g sin theta is the acceleration. So, g sin theta is directed towards the mean position, and we will see also in this case that it is proportional to the displacement. Sin theta can be written as proportional to our displacement x, then it is also proportional. So, in all these cases it will be called a simple harmonic motion. Similarly, the mass spring system also undergoes whether vertical or horizontal. In both cases it performs simple harmonic motion. In all these simple harmonic motion case, we can define as before the periodic motion, because it is a periodic motion, it has a time period, the time after which the motion is repeated, that is our time period. So, time period of a simple harmonic motion is the time taken to complete one oscillation. Now, I can say that it is the time taken to complete one oscillation, because it is oscillatory, but periodic case re mu oscillation kahilini. I said that it is the time after which it is repeated, because in periodic motion not necessarily oscillatory, but because this is oscillatory also, I am saying that it is the time taken to complete one oscillation. And as before, the frequency, we define the frequency of the oscillation. Frequency is number of oscillations in 1 second in unit time. So, if it is represented by capital T, it is represented by f, which is 1 by T, as before it is also Hertz, and its dimension is T inverse. So, frequency, time period. Then I can represent displacement, or let me write before that amplitude. The maximum displacement of the body from mean position. In the case of simple pendulum, I showed you that it moves from B to A. Again, it maximum A पर्यंत जाउची. तामाने B to A से distance टा is its amplitude. So the maximum displacement. Then the displacement. I told you already, displacement may be position displacement, or it may represent the pressure variation, or it may represent any other quantity of that problem in hand, or anything which is undergoing a simple harmonic motion. Suppose the charge on a capacitor changes with time, which is simple harmonic, then we will say that there the charge is the amount of charge present on the plate of a capacitor in an AC circuit is simple harmonic, then it is represented by a displacement vector. So we say the displacement. Now in all these cases, they are represented by periodic functions, and the simple functions are the very simple functions. Some of the simple functions are the sine and cos. If your function is, let us say, x is equal to a sin omega t, or it is, or say b cos omega t, or cos function a and b are constants, or a linear combination of sine and cos function. That means something like a sin omega t plus b cos omega t. This is also a, these are all functions which represent simple harmonic motions. The displacement, where x is my displacement vector. Now what is omega? So omega is called the angular frequency. Is omega, which is nothing but 2 pi by t, 2 pi f, which is 2 pi by t. See, in these cases of sine and cos functions, if you remember the sine and wave functions graphs, the sine graph is like this. This is your sin omega t. That is, it is 0 at 0, at pi by 2 it is maximum, let us say 1, mu a multiply karji with a heijibo seta. So this is the maximum. This is on the negative side, it goes to the minus 1. So this at pi it is 0, at 3 pi by 2 it is minus, this is 3 pi by 2, it is negative maximum, and again at 2 pi it is 0. If I draw it further, it will be repeated. This same sine graph is after this interval of time t, sorry, not from here, here. After this time interval, the motion is repeated. So a sine function represents a repetitive function, it is a periodic function. After what time interval? In angle it is 2 pi, in terms of time it is t. So 2 pi by t will be the angular frequency. Omega into t is equal to, when omega t is equal to 2 pi, again the same thing, एठी 0 थिला जहा एठी भी 0 अच्छी displacement. So after time t, when t is equal to t जगह capital T लिखिली, when omega t small t जगह मु capital T लिखिली वर्तमान. So when omega t is equal to 2 pi, the motion is repeated. So my omega is equal to 2 pi by t. So from that I get 2 pi f, and it is called angular frequency. So if the displacement, if the body is undergoing a simple harmonic motion, we find that the displacement satisfies this function, the sine function or a cos function or a combination of this. Why this combination? Cos. If you go into the cos, if you write it here, the cos function is when it is 0, omega t is 0, let me write it as omega t. So, when omega t is 0, cos is maximum plus 1. When it is pi by 2, it is 0. When it is pi, it is minus 1. When it is 3 pi by 2, it is 0 back. When 2 pi, it is plus 1. So, this is my cos function, cos omega t. So, cos omega t, you can see that from here to here, this is, there is only a pi by 2 difference between mu eiठु जदि आरंभ करी थांती ए ग्राफ एठु आरंभ करी थांती एठी सारी थांती then a same graph पाई थांती. Now beyond that mu 2 pi ପରେ जदि करिबी again I will see that this same graph is repeated. It becomes 0 here, then goes to a maximum, then comes back to maximum plus 1. Here when it is 0, this comes to plus 1. So 2 pi eta 4 pi पर्यंत मु draw कली. So you see that from here to here, this motion is repeated. So this time interval is its period, time period. So cos function and sine function, they are periodic functions, and our simple harmonic motion can be represented by these functions. Now what about this one? What is the graph of this one? Or in fact mathematically I can show that this is also a periodic function, because let our A is represented as d cos phi and B let me write as d sin phi. यार वैल्यू तो प्लस 1 रु माइनस 1 भितर ता संगे मु d मल्टीप्लाई कली. So if A and B can be, I just assume d is some constant, d is some constant, phi is some angle in radian. All these angles are measured in radians. So be careful, it is not degrees. So a sin omega t. Now a जगह मुझे d लिखी d cos phi sin omega t. Let us put that here. It becomes d cos phi sin omega t plus d sin phi cos omega t. That becomes equal to, d is common. Now sin a cos b plus cos a sin b. So that is nothing but sin a plus b. So omega t plus phi. So only this phi comes. Phi is the constant phase or initial phase. I will tell you what is phase. This whole quantity, this angular quantity is phase total, and the initial, that means when t is 0, the phase is phi. So phi is my initial phase. Initial, that means at time t is equal to 0. So it can be, this linear combination can be written as a sine function in this manner, where d ra value kete, d is, if I square a square plus b square will be d square cos square phi plus d square sin square phi. Teno d square ta common he gala, cos square phi sin square phi misi gale 1 he jibo. So a square plus d will be equal to root over of a square plus b square. If you square this and add, square and add, you get d square is equal to a square plus b square. From that I have written this, and phi is, this is sin omega t plus phi. What is phi? Divide this, b by a. So b by a is equal to d kati jibo tan phi. So my phi is tan inverse b by a. So any linear combination of sine and cos can be written as this function. So sine function is periodic, that you already know. So this can be written as a sine function. I can write it as a cos function also. इफ आई राइट मु डी cos phi जगह एटा को डी sin phi नहीं थांती हेले से ही थांता sin a sin b plus cos a cos b हेले सेटा cos रो फंक्शन हिसाब रे ही थांता. So you can see that all these functions are periodic functions, and these periodic functions can represent a simple harmonic motion also. Now I mentioned the word phase. Now in a simple harmonic motion, what is phase? Phase is a quantity which tells us, which determines, it is a quantity which determines the state of the particle undergoing oscillation in oscillation with respect to its position, determines the state of the particle in oscillation with regard to its position and direction of motion. Let us take the example of the simple pendulum. These are the two extreme positions. We call them extreme position. Let me say this, one of them is towards the positive side, the other will be towards the negative side, and the 0 position, or this is my mean position. This is one extreme position, this is another extreme position, or I will say that this is the positive extreme position, this is the negative extreme position, and this is the mean position of the simple pendulum. The maximum displacement, that means maximum distance it has moved, that is its amplitude. So, the amplitude is that. Now, this is a quantity if my x is equals to a sin omega t plus phi. I said that this total angular, this angular part or the argument of sine, this argument is phase. This can be represented in the form of either in radians, in terms of pi, some multiple of pi, some multiple, not necessarily a whole number, it may be some multiple of pi, Usually it is represented as multiples of pi, or it is as fraction of t. That means, suppose I say that the phase is 0, it tells me that the angle is 0, this angle is 0, a sin, that means the x is equal to 0. So, if I put the phase ता माने omega t plus phi equals to 0, ता माने x is equal to 0, which tells me that the body is at mean position. And because it is 0, I say that it is going towards positive maximum, positive extreme position. But when I say phase is equal to pi, again omega t plus phi is 0, phi is equal to pi, again that sine of pi will be 0. So, this if I put, then x will be again 0. but then what is the difference between the two things? If you look at the sine graph, when omega t is 0 or omega t plus phi is 0, it is at 0. Again when it is pi, the value of the displacement is, which is on the y axis, is again 0. But what is the difference here? Here the particle is trying to go to this side. Again when the particle comes from here A to B and it goes to this position, initially the body started in this direction. At that point phase was 0. So, this is the position, but when phase is pi means it is again at B, but the body is moving in the opposite direction. It is moving towards the other extreme position, not to the first A position. It is going towards the C position. So, this is the difference between the phase 0 and pi. So, that means तापर से एमती नेगेटिव आड़कू जाउची, the particle is moving towards the negative directions. So, that is the difference. That means the body is again at mean position, but moving towards negative extreme position. This is the difference between 0 and pi. Now, if I say, or I can call this also the time period t by 2. In terms of time period, it is equal to t by 2, because if you start from here, the time taken to go to A, back to B, C, again to B. So, जोठू आरंभ करथिबो सेठी पहुँचीबा पई जतिकी टाइम नबो सेटा हला टाइम पीरियड. तेणु बी रु आरंभ करथिबो ए को जीवो, बी को आसीबो, पुणी सी को आसीबो, पुणी पूरा पूरा कंप्लीट रोटेशन जीवा दर, कंप्लीट ऑसिलेशन दिया. बी रु जाई किरी आउ थरे आसिला सेटा हाफ टाइम पीरियड. पुणी सी को जाई किरी पुणी बी को आसीबो, तेबे जाई किरी एटा हमर कंप्लीट ऑसिलेशन हला. सो कंप्लीट ऑसिलेशन पई टाइम पीरियड हला टी. ता माने बी रु ए को गला, ए रु बी को आसिला, ता माने हाफ टाइम पीरियड. So, this is pi is same thing as t by 2. So, you can represent the phase as some multiple of pi or some fraction of t by 2 एठी. So, if phase is, let us say phase is equal to मु धर एठू एतिकी आछि, ता माने गोटे पार्ट गला सेकेंड, ता माने टोटल पार्ट को मु चारि भाग जदी करिवि टाइम पीरियड एठू एतिकी जिया पई t by 4, जदी t by 4 बा pi by 2 एठी pi by 2 समय रे it is at the positive extreme position plus a, एटा हबो minus a, where a is my amplitude, this is amplitude, the maximum displacement. When this argument, this is pi by 2, sin pi by 2 will be 1. So, x will be equal to a. So, in this position my x will be equal to a, whether time put kale bhi seya. So, x will be equal to a, but it is now moving towards the mean position, going towards mean position. So, the phase is a quantity, or it is an angle actually. It is a quantity which tells you where the particle is during its oscillation and in which direction it is moving, whether it is moving towards the mean position or it is moving away from the mean position towards the one extreme position. That can be known from the phase. So, that is what we mean by the phase of a oscillating particle. So, if I say that it is 3 let us say 3 t by 2, ता माने t by 2 तीनटा बेसी गला, ता माने गोटे t, दिस इज इक्वल टू t प्लस t by 2. ता माने एठू जदी आरंभ करिथिबो गोटे थर गला एमती गला एठी कंप्लीट हला t गला आउ t by 2 माने t by 2 एठी को जाई कि पुनी फेरिला एठी अछि, ता माने बॉडी आउ याड को जाउछि. सो फ्रॉम दैट यू कैन नो द फेज. सपोज आई से दैट फेज इज t by 8, or let me say t by pi by 4. एंगल हिसाब रे कहले pi by 4, टाइम हिसाब रे कहले t by 8. सो पूरा टोटल t रो 8 भाग, ता माने एठू एते कि जिया t by 4 दरकार, तार अधा, ता माने समवेयर हियर. सो द पार्टिकल इज समवेयर हियर एट t by 8 टाइम. सो बट एठू एतिकी बाटा जाईची, ता माने सियाड को जाउची. So याड को जाउची going towards the positive maximum and it is at this position. So once you know this phase, you can know the state of the particle, what is the in which position it is and which direction it is moving. So phase is very important. In many cases we start with phi is equal to 0. That initial phase is 0 let us say. तामाने टाइम आमे जोठू मेजर करूचु सेही पोजीशन टाको आमे 0 पोजीशन बोली धरिबा तबे योर phi will be 0. मीन पोजीशन टाको आमे धरिबा जदी so the displacement in SHM can be written as, let us say, A sin, this is a general formula, omega t plus phi, where phi is the initial phase. What I mean by initial phase is that at time t is equal to 0, phase is phi. तामाने मु जदि धर इन केस ऑफ सिंपल पेंडुलम मु आनिले एठू आनिके छाड़िली प्रकृत रे एटा मीन पोजीशन नुहे तेणु मीन पोजीशन टा एटा आमे मीन पोजीशन रा जेतेबेले अछि सेतेबेले जदि टाइम t इज इक्वल टू 0 बोली धरिबा तेबे एठी मु जेतेबेले छाड़िली सेइठू जदि टाइम काउंट आरंभ करी तेबे मु कहबी जे इनिशियल फेज हला एठू एतिकी ऑलरेडी जाई सरची ता माने एटा केते हला एठू एतिकी पाई बाय 2 सो एठी phi is equal to pi by 2. I will say that the phase of the particle initial phase pi by 2 रे थिला कारण से मीन रे नाही मीन टू से केते एंगुलर ऑलरेडी आगो को जाईची बारी ना pi by 2 रे अछि सेइठू मु टाइम मेजर करी किंतु मु जदि टाइम एठू मेजर करी धर मीन जिते बड़े ये बी को आसला मु आग ऑसिलेशन आरंभ करदेली से बॉडीटा ए रु बी को आसला बी रु सी को गला सी रु बी को जिते बड़े आसला सेते बड़े मु आरंभ करी मोर घंटा आरंभ करी आउ टाइम सेठू मापिबी ता माने मोर मीन पोजीशन रे अछि बॉडीटा ता माने x इज इक्वल टू 0 एट टाइम इफ आई टेक x इज इक्वल टू 0 एट टाइम t इज इक्वल टू 0 ता माने t को 0 पुट करी x को 0 पुट करी ता माने a is not 0, so phi must be 0. That gives me phi is equal to 0. So we will take that initial time एमती आमे measure करूचु आमे mean position रो time measure करूचु then we will say that the initial phase is 0 if time is measured from the mean position. Time measured from mean position. So if this is your displacement, what is the velocity of the body? Oscillating body will be equal to v will be equal to the time derivative of x. So I take the time derivative. If you derivate it, and I for all cases I take phi is equal to 0. So my xt is actually equal to a sin omega t. For simplicity or for convenience, I have taken this phase to be 0 by taking the time is measured from the from the mean position. When the body is at mean position and going towards the positive maximum, I am saying my time is 0. So dx by dt will be a sin omega t ro differentiation will be omega cos omega t. So this will be omega cos omega t. So I can write it as omega times a cos omega t. Now a cos omega t टा a sin omega t रु बाहर करी केमती ना 1 माइनस सॉरी a माइनस a स्क्वायर माइनस a स्क्वायर sin स्क्वायर ओमेगा t. दिस विल बी a स्क्वायर कॉमन नहीं जा 1 माइनस sin स्क्वायर ओमेगा t 1 माइनस sin स्क्वायर ओमेगा t इज cos स्क्वायर ओमेगा t तेणु यार वैल्यू है a स्क्वायर cos स्क्वायर ओमेगा t तार रूट ओवर नहीं गले हे जो मोर a ओमेगा a cos ओमेगा t. So this is a cos omega t. So this is equal to omega times square root of a square minus x square. So this is velocity of the body. What about acceleration? The acceleration of the body will be the time derivative of velocity. So, I take the time derivative of velocity, याकू differentiate करो ना cos omega t को differentiate कले आसीबो minus a omega आगुरु थिला cos omega t रो derivative हैला minus omega sin omega t. So, this gives me minus omega square a sin omega t. So, that means this is equal to minus omega square x. So, acceleration is minus omega square x, velocity is omega times a square minus x square. You can see that in this function acceleration is proportional, this is a constant, omega square is a constant. So, your acceleration is proportional to x or displacement. In the case of mass and spring, a spring is attached rigidly to the wall and a mass is attached at this end, then the mass is displaced to some point, to a little distance away from it and left. Tamane you are extending this to A by an amount A. Then you are extending the spring by an amount A. When you are extending the spring by an amount A and releasing it, gradually the spring will try to compress, it will come back. So, the body will move to this side, it will come to this point position A, B, this is my A position, and it will again at some point you will see that it will be compressed, the spring will be compressed and come to some position here, the mass comes to this point. This is another extreme position, the other extreme position, this is the mean position, this is one of the extreme position. I am not up to scale, this should be equal to this. So, it goes to other extremum A, this is the B position, this will be its C position. So, the spring mass motion, mass is moving to and fro about the mean position, and this also can be written in this manner. From this I can say that in this case, in SHM, I can write an equation of SHM a simple harmonic motion, that your acceleration has to be proportional to displacement and towards the mean position. Displacement is always measured from the mean position, किंतु acceleration is always towards the mean position. तेणु मु एठी नेगेटिव देली, एटा भी वेक्टर जदि कहबा तबे acceleration is minus displacement direction न नहीं करी बर्तमान जदि लिखिबी. सो मास जदि मल्टीप्लाई करी दुई पटे ता माने फोर्स इज आल्सो प्रोपोर्शनल टू displacement. Wherever you get this and towards the mean position, it is proportional to displacement from mean position and it is directed towards the mean position, then it is also called the SHM. Same katha, acceleration kuha ki force kuha, because force is nothing but mass into acceleration, mass is constant, then gote constant ta multiply kale bhi proportionality rahibo. So, force is proportional. See, in the case of mass spring system, you know that when a spring is extended by x distance or x, then force in the spring is equal to minus kx. This you have read from your elasticity chapter, Hooke's law. There will be a restoring force. This force is called restoring force. Why it is called restoring force? Because it tries to restore the position. That means it is always towards the mean position. So, restoring force brings the body towards mean position, brings body back to mean position or mean condition कहि पार or mean position. That is why it is called restoring force. The force that comes into play which tries to bring the body back to the mean position is our restoring force. So, the restoring force is proportional to x and directed towards the mean position. So, this satisfies our simple harmonic motion case. So, that is force is equal to mass minus k into x. Now, force can be written as mass into acceleration. को कहार मास जो बॉडी एसएचएम करूची तार मास तामाने एठी एई मासटा स्प्रिंग रो मास नुए स्प्रिंग इज मासलेस हम एठी धरिचु एठी भी सेमती स्ट्रिंग इज मासलेस द स्ट्रिंग जो थ्रू ओळा हेची से सिंपल पेंडुलम टा इज मासलेस बट मास होची हमर एई बॉडी रो मास. सो मास इनटू एक्सेलरेशन ना एक्सेलरेशन इज तामाने मास जदी मु m धरिबी एक्सेलरेशन इज dv by dt रेट ऑफ चेंज ऑफ वेलोसिटी. रेट ऑफ चेंज ऑफ वेलोसिटी होची कोन ना m d by dt वेलोसिटी कोन ना वेलोसिटी होची dx by dt. तबे मु याकु लिखिबी m d square x by dt square. So force is equal to, so this gives you the equation for SHM, that m d square x by dt square, this is force, is equal to minus kx, or if I bring to this side, this becomes m d square x by dt square plus kx equals to 0, or I get d square x by dt square plus k by m into x equals to 0. We write, let us write k by m as omega square. So, this is the usual normal conditions, usually we write omega square x is equal to 0. This is a differential equation. Now, if you will read the differential equations, there is which function which will satisfy this equation. That we have said, found that our x equals to, our solution of this are some constant time sin omega t or some constant time cos omega t, or I had said the linear combination as before, or a linear combination. Of cos sin omega t and cos omega t, that I have told. So, this is the equation differential, this is the differential equation, or you can actually, these things can be written as e to the power I omega t. You will read later on that this is where I is a complex quantity iota. So, e to the power I omega t, or this function is also the combination of sin and cos. So, these are the solution, these will be the solutions. I have already used x is equal to a sin omega t plus phi, because a linear combination is more general. So, that is why I took a sin omega t plus phi, and we found out the velocity, the acceleration. Then we go to the energy, the mechanical energy, total mechanical energy. Now, mechanical energy consists of the kinetic energy and the potential energy. So, kinetic energy will be equal to half mv square. So, half m v square, v is velocity. So, I am saying bahar karthile velocity. If you remember, I wrote x is equal to a sin omega t, v will be equal to a omega cos omega t, and our acceleration was minus omega square a sin omega t. These are the things that we have already found out. So, half mv square will be equal to half, and this can also be written as, I wrote it beforehand, use that velocity value m v square, सेठी जदि एटा को लिखिथिली मु ओमेगा रूट ओवर ऑफ a square minus x square. So, तार square half m v square is omega square into this. is kinetic energy. Potential energy will be, this is potential energy. Will be half kx square, the energy stored in a spring is half kx square. So, this will be half k, k is, I have written k is equal to m omega square. So, k is equal to m omega square into x square. If you add them, kinetic energy plus potential energy, what I get is half m omega square s square. So, which is a constant. So, total mechanical energy in the case of a simple harmonic motion is always constant. So, we will continue with this next class.